Pariksha channel. Today we'll solve some more problems of diode circuits from analog electronics. Okay. Now we'll see the question. If the input voltage applied to the circuit in the sine wave with an amplitude of 12 volts peak to peak sine waveform, then the output voltage is okay. Now he's telling that input voltage is the sinusoidal waveform of 12 volts peak to peak. 12 volts peak to peak in the sense the positive peak is 6 volts and negative peak is also 6 volts, that is minus 6 volts. Total, it is 12 volts peak to peak. Okay. Now, if you see the given circuit is acting like a half wave rectifier. This is the diode and this is the resistor R, and input voltage is a sinusoidal waveform. So the diode conducts only during the positive half of the cycle. The diode conducts only during the positive half cycle. So the output will be like this, only the positive half cycles. The negative half cycle, it will be 0. Diode is switched off, acts like an open circuit, so the output is 0. And again, the next half cycle, next positive half cycle will be there. So it's basically half wave rectifier with the positive half cycles. So the output is, this is minimum is 0 volts and maximum is 6 volts. So it is 6 volts peak to peak. Answer is option A. Now we'll see the next question. The output DC voltage of a full wave rectifier is, here he's asking the average output DC voltage of a full wave rectifier. Okay. Now we'll see, we have two types of full wave rectifiers, that is center tapped full wave rectifier. This is the center tapped full wave rectifier, where we have two diodes, diode D1 and diode D2, and load resistance in between. There is a tapping in between. There is a load resistance here. Okay. So input waveform is the sinusoidal waveform. Here, during the positive half cycle of the input waveform, D1 conducts and current flows through RL in this direction. During the negative half cycle of input voltage, D2 conducts, D1 is off and D2 conducts. So current flows through RL. So if you observe, during the positive half cycle of the input and negative half cycle of the input, current flows through the load resistance in the same direction. So the output voltage will be like this. During the positive half cycle, it is a positive voltage, and during the negative half cycle also, it is a positive voltage in the output because the same direction of the current flow. This is output voltage. So here it is 2 Vm by pi. And if you observe carefully, diode D1 and D2 both do not conduct simultaneously. So during the positive half cycle, D1 conducts, and during negative half cycle, D2 conducts. So there will be the diode drop also. So it is IDC into RF. Okay, RF is the diode forward resistance. Diodes forward resistance. Okay. So at the same time, only one of the diodes will conduct. That's why we are taking only the single diode drop. We are not taking two diode drops. In case of a bridge rectifier, if you see the bridge rectifier, here we have 4 diodes. This is the primary winding and this is the secondary winding. Here we have 4 diodes, D1, D2 and D3, D4. All these are connected in a diagonal shape. Okay. In between resistor is a load resistance RL. This is D1, D2, D3 and D4. If you observe the operation of this circuit, during the positive half cycle of the input voltage, diode D2 and D3 conducts. Here 2 diodes are conducting for simultaneously for positive half cycle. Similarly, for the negative half cycle, if you see, diode D1 and D4 conduct simultaneously. So in this case, we have 2 diodes, a voltage drop across 2 diodes. Okay, voltage drop across 2 diodes will be coming into the picture. So output voltage in this case will be, the average voltage will be 2 Vm by pi minus IDC into 2 RF. Forward resistance will be twice. This is in case of bridge circuit. In case of a center tapped circuit, it is only single RF. Okay. In the given options, there is no 2 RF in any of the options. So answer is option A, 2 Vm by pi minus IDC RF. We'll see the next problem. So what will be the average voltage of the circuit. So if you observe the given circuit is a half wave rectifier. This is nothing but a half wave rectifier. Okay. Now we'll calculate the IDC for half wave rectifier. Okay. I average is equals to the formula for I average is 1 by 2 pi integral of 0 to 2 pi I d theta. Okay. This is nothing but the average value is the total charge per cycle divided by the time period. The time period is 2 pi here. So for the half wave rectifier, diode conducts during the positive half cycle, and sorry, here the diode is in the reverse direction. So we have to consider that during the positive half cycle, the diode is off, and during the negative half cycle, diode conducts. During the positive half cycle, again it is off, and negative half cycle, the diode conducts. So the overall time period will be 2 pi, 0 to 2 pi. But the conduction period is pi to 2 pi. You have to do like this. Okay, this is the conduction period. So now I average is equals to 1 by 2 pi 0 to pi I d theta plus pi to 2 pi I d theta. As 0 to 2 pi is a non-conduction period, this becomes 0. Now 1 by 2 pi to 2 pi. The conduction is I, current. I am sin theta d theta. So if you integrate that 1 by 2 pi, I am integral of sin theta is minus cos theta 2 pi pi. So if you substitute these values, you will get the answer Im by pi minus. So this is the current. Okay, Im by pi is this is the current. So he's asking for VDC, average voltage. So average voltage is nothing but Im multiplied by the load resistance RL. That is minus Im by pi RL is equals to minus Vm by pi. So the answer is option A. Now here, the equivalent DC output voltage of the half wave rectifier is dash the equivalent DC voltage of full wave rectifier. If you see for the half wave rectifier and full wave rectifier, the average voltage VDC is equals to, this is Vm by pi. This is 2 Vm by pi. Similarly, IDC is equals to Im by pi. This is 2 Im by pi. If you take if you see these two things, the half wave rectifier has half of the value of full wave rectifier. So the answer is option B, half. The rectifier which requires minimum amount of the filtering. So see here options given is half wave rectifier, full wave rectifier, voltage doubler circuit, and SCR half wave rectifier. If the option C will not be considered because it is not a rectifier, it is a doubler circuit. So available options are these two and this. If you see the waveform, output waveform of the half wave rectifier and full wave rectifier, this is the half wave rectifier output. During the positive half cycle, it conducts. Negative half cycle, it does not conduct. For the positive half rectifier and for the full wave circuit, full wave rectifier, it conducts for 2 half cycles. So output will be like this. Okay. Now, if you observe carefully, while filtering action, during the filtering action, it happens like this. This is the filtering action. The capacitor charges to the peak value and it discharges slowly. And again it charges and discharges slowly. It charges and discharges. This is the filter output. This green color lines, thick lines of the filter output. For the full wave rectifier, it will be like this. Capacitor charges and discharges. Charges and discharges. So if you observe in this, the peak to peak value of the ripple voltages, here this one and this one. The peak to peak value of the ripple voltage for the half wave rectifier is higher. This means higher ripples. For the full wave rectifier, the ripples are reduced. So it has lower ripples. Lower ripples. The ripple peak to peak voltage of the ripples is very less. So if you see the rectifier which requires minimum amount of filtering is, that is full wave rectifier. So the answer is option B. Full wave rectifier needs a minimum filtering, whereas half wave rectifier requires more filtering, more filter circuits are required. We'll see the next question. The percentage regulation of a half wave rectifier. This is simple. The percentage regulation is no load minus full load divided by full load into 100. This is the formula. Okay, so the answer is option C. No load minus full load divided by full load. This is the formula of the voltage regulator. They have asked for half wave rectifier. Anyway, the formula remains same. Yeah. Now we'll see the next problem. The circuit shown in the figure is basic. So if you see the circuit, this is a clamper circuit. We'll see the operation of this clamper circuit. Okay. We have two types of clampers. One is a positive clamper and negative clamper. Now we'll see the operation of this clamper given in the circuit. This is the resistor R and this is the diode D. And this diode contains a forward resistance RF. Here it is not given, but you remember the diode contains a forward resistance RF. Okay. Now we'll see the operation. Now we have to observe this carefully. Input voltage is sinusoidal waveform. Input voltage is a sinusoidal waveform. During the positive half cycle of the circuit, the diode conducts. Diode conducts. So during this conduction process, there is a voltage developed across the capacitor, and the capacitor charges to the voltage Vm. Vm is the maximum voltage of the input cycle. This happens during the positive half cycle. Now, during the negative half cycle, so during the positive half cycle, what happens? Diode conducts, diode D1 conducts, and the capacitor charges. Capacitor C charges to voltage Vm voltage. So during the negative half cycle, the diode does not conduct, but the voltage across the capacitor will be there. There is a voltage across the capacitor like that, and the diode does not conduct. This is the resistor R. Diode acts like an open switch. So if you observe from here, this is input voltage V in, and this is output voltage. So now if you apply KVL from this point, the output voltage will be Vout will be minus Vm plus Vin. Okay. So the first cycle, sinusoidal waveform, when the input voltage is applied for the first cycle, what happens is positive half cycle, the diode will be charged. From next cycle onwards, if you observe the output will be minus Vm, the voltage across the capacitor C, plus V in. This will be the output voltage. So means what happens is you are shifting the base voltage to minus Vm. You are just shifting the base voltage to minus Vm. So the output waveform will be like this. Output waveform will be like this. This is the zero base. You are shifting this zero base to minus Vm. Now this will be the new base voltage. Minus Vm plus V in. On that the Vin starts. This is sinusoidal waveform. So the sinusoidal waveform originally, which is on the zero bias, like this, which is on the zero bias, has shifted to, this is the input voltage, which is on the zero bias, has shifted to minus Vm bias. So this is nothing but a negative clamper. You are clamping the DC bias voltage of the input, DC bias of the input voltage to the negative side. So this is the negative clamper. So the answer is option B. It is a clamping circuit. If you observe similarly the positive clamper, this is a capacitor. You have to reverse the diode direction. If you reverse the diode direction, this will be the positive clamper circuit. The output will be minus Vm. The output is nothing but output will be plus Vm plus Vin. Why plus Vm? Because the diode conducts in the negative half cycle. Diode conducts in the negative half cycle in this direction. So the voltage across the capacitor will be stored like this. And input voltage is here. So both are in the same direction. So Vm plus Vin will be the output voltage. So here in case of positive clamper, the output voltage waveform will be like this. This is the new base voltage, that is plus Vm, and the output waveform will be like this. Hope you understood this. Now, in this concept, we can continue this explanation. In this concept, if you observe carefully, there is one more question followed by the output voltage waveform for the positive clamper. If you see output waveform for the positive clamper, this is 0 and this is a new base, that is plus Vm. The positive half cycle goes practically, it will go till 2 Vm minus V cut-in voltage, diode cut-in voltage. So here negative, it will go till cut-in voltage. This is the cut-in voltage of the diode. So it will be like this. So if you observe carefully, the area under means cut-in voltage in a sense. What does it mean? The diode is in the conduction mode. Diode is conducting during the negative half cycle. In case of positive clamper, this clamper, if you observe carefully, this clamper, if you observe carefully, diode is conducting during the negative half cycle. Okay, so that portion is taken here. Means for this portion, the resistance offered is RF, diode forward resistance. Diode forward resistance. For the remaining form of the portion, for the remaining portion, that is this entire portion, if you see, the resistance offered is R. The resistance offered is the load resistance R, whatever mentioned here, this R. Okay. So now, if you take the ratio, if you take the ratio of these two areas, the area, this area, and this entire area, it remains approximately equal to the ratio of these resistances also. That's what he's trying to tell. So the area under the area under the waveform when diode is forward biased divided by area under the waveform when diode is reverse biased is equals to the forward resistance of the diode divided by the load resistance. Okay, this is what he's trying to do. So the answer for this question is now AF by AR divided by RF by R. Answer is option B. Okay, hope you got this explanation of the positive and negative clampers and this area proportionality formula. Now we'll see the next circuit. A sinusoidal wave of amplitude Vn is applied as input to parallel diode clipping circuit. So what is the output voltage? Now I would like to explain one basic formula here. See, this is the resistance R. This is the diode. Now we'll see without this VR. In the question VR is given, I am taking the circuit without VR. Okay, because you should understand the basic thing. Input voltage is sinusoidal waveform. So what will be the output voltage? Output voltage will be like this. So during the positive half cycle diode does not conduct. During the negative half cycle diode conducts. So negative half cycle will not appear, ideally speaking. So output voltage like this. What is the base for this output voltage? 0 is the base voltage. Okay, this will be Vm, maximum voltage. Now you are applying a positive bias to this circuit now. This is R and the same diode in the same direction. You are applying a positive bias, that is VR. Okay, to this circuit. Now what happens to the base voltage? And you have applied input voltage sinusoidal. Now here in this case, what happens to the base voltage? The base voltage will be shifted. The base voltage will be shifted to plus VR because the applied voltage is plus VR, not minus. Applied voltage is plus VR. So the base shifts to plus VR. So the output voltage will be like this. Only that positive clip, that positive portion will come into the picture. The remaining portion will be cut off. The remaining voltage will be terminated. Originally, this is the waveform, but now you are taking only the upper portion. This particular, you are shifting the base to plus VR. So only this portion will be there in the output. In this case, if you see, so output voltage will be this. So output voltage is between VR and VM. This is the answer. So, so the output is allowed in between VR and VM. Option A is the answer. Similarly, if you see, I would like to continue this explanation with different circuits because tomorrow they may twist the question like this. For the same circuit, this is resistance R, and diode D. They have given negative VR. What will happen? Just guess. This is the negative VR. Now the base is shifted to the negative side. Now the base is, this is 0. Base is shifted to the negative VR side. So now the output voltage will be like this. Positive portion, positive half cycle, and a part of negative half cycle also. Positive portion and part of negative half cycle. So now the output varies from minus VR to plus VR. Okay, whenever you apply, whichever bias you apply, the base will be shifted to that particular portion, and the base will be shifted to that particular side, and the additional portion will be added to the sinusoidal circuit. Either added or cut off. It depends on the base voltage. So we'll see the next question. For the circuit shown in the figure, find V out, output voltage, and diode current D. So the current flows in this direction, he has already given. So applying KVL, by applying KVL, you will get voltage E, input voltage, minus silicon diode drop, that is 0.7 volts, and next is a germanium diode drop, that is 0.3, and minus resistance R into I is equals to 0. Okay. So here IR is nothing but output voltage. So input voltage 12 minus 0.7 minus 0.3 minus resistance is 5.6 into 10 to the power of 3 multiplied by I is equals to 0. So I is equals to 11 divided by 5.6 into 10 to the power of 3, which is equals to 1.96 milliamps. So this is current I, whereas output voltage V0 is equals to 1.96 milliamps multiplied by 5.6 kilo ohms, which will be approximately equal to 11 volts. So the answer is option C. Now for the next question, for the Zener diode, if the temperature is increased to 100 degrees from room temperature, okay, boiling point of water, the change in the Zener potential will be, okay, the temperature is increased from 25 degree to 100 degree. So this is T0 and this is T1, okay, and he has given the temperature coefficient of the Zener, that is temperature coefficient Tc is equals to 0.072 degree per centigrade. Fine. Now he is asking what is the change in the Zener voltage, Vz, delta Vz. So we'll see the formula, delta Vz, change in the Zener voltage is equals to temperature coefficient multiplied by Zener voltage divided by 100 degrees centigrade T1 minus T0. This is equals to 0.072 multiplied by Vz is given as 20 volts in the question. The 20 volts is not ever hit. So 20 divided by 100 degree multiplied by 100 minus original temperature is 25. If you calculate this, it will come around 1.08 volts. So the answer is approximate. Answer is option C. The Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.